So here in this question we are given that this airplane accelerates from rest at one end of the runway and it must attain the takeoff speed before reaching the other end of the runway, and we have to calculate the minimum length, this delta x, required for the runway so that the airplane can take off easily. Now let's first discuss the important topics related to this question, and then we'll get back to this question at the end of the video. Welcome to STEM Professionals. In this video we'll discuss two important topics. The first one, position as a function of time and acceleration. The next one is velocity as a function of position. So let's start with the video. Now in the last video we derived these two equations, this one and this one, and if you haven't seen that video, click on the bell icon to see it. Now the first equation that we derived was v is equals to v naught plus at, and the second equation was x is equals to x naught plus 1 over 2 v naught plus v multiplied with t. So these the two equations we derived in the last video. Now in this video we'll derive these two equations. First we'll start with the third one. So we'll be using these two equations that we obtained in the last video to derive the third equation, which is position as a function of time and acceleration. So we can do one thing, we can put the value of v in the second equation. So this would become x is equals to x naught plus 1 over 2 v naught plus, now we have v naught plus at multiplied with t. Now we can simplify it further, so we'll get this would be equals to x naught plus 1 over 2, this would become 2 v naught, this would be at, and we can do one thing, we can multiply t here, so this would become t square, and here it will be t. So this would be equals to x naught plus v naught t, this is t here, v naught t, then plus 1 over 2 a t square. So this is our third equation. Now let's understand one more concept that you may use while solving numericals. So we have this VT graph, and let the velocity of the particle at time t equals to 0 be v naught, this is v naught here, and at any time t the final velocity becomes v. Now I'll be showing that the distance traveled by the particle during this time interval will be equals to the area under this curve. This total area would represent the total distance traveled by the particle during this time interval, and to show that I'll be taking the reference of this question that I discussed in the last video, and if you haven't seen this video, click on the bell icon to see it. Now in that question, the velocity of the initial velocity of the boat, that is v naught, it was 1.5. So this was, we can write this is 1.5, and the velocity at time t equals to 5 seconds, it was 13.5 meter per second. So let's find this total area under this curve, and this would be, we can split into two areas like this. Now this, the upper area is in the form of triangle, so area of the triangle will be equals to half base into height. So base we have 5 minus 0, which is 5, so this is 5 second, 1 over 2 as it is, multiplied with height. Now height we have 13.5 meter per second minus, this is 1.5 meter per second. This would be the height, the difference of this. Now this would be equals to 30 meter. So this is area A1. We can take this area to be 1 and this to be second. Now the area A2, it is in the form of rectangle. So area of the rectangle is length multiplied with this width. So length we have 5 second and width we have 1.5. So 1.5 meter per second. So that would be equals to 7.50 meter. Now if you add these two area, A1 plus A2, this is 37.5 meter, and this is the same distance that we obtained in the last in the last video. Let me show it also. So this is the same distance. This is 37.5, and there also we have obtained the distance to be 37.5. So we can conclude that the distance traveled by an object from a time t1 to t2 is equals to the area under the curve on velocity versus time graph. Now let's take an example which is based on third equation that we have derived. Now here we are given that a drag racer starts from rest and accelerates at 7.40 meter per second squared. Now we have to calculate that how far it has traveled in 1 second, 2 seconds and in 3 seconds. So here we see that the drag racer starts from rest. That means its initial velocity v0, it should be equals to 0, and it accelerates at 7.4 meter per second squared. This is the acceleration which is constant throughout the motion. Now this is the position of the drag racer at t equals to 0. This is at t equals to 1. Similarly, t equals to 2 seconds, and this is t equals to 3 seconds. Now since acceleration is constant, so we can use this equation that we have derived. That is the third equation, which is x is equals to x naught plus v naught t plus 1 over 2 a t square. Now since acceleration is this velocity is 0, so this term would be 0, and the body starts from this point, that is from origin, so x naught will also be 0. So in this particular case, this equation reduces to x is equals to 1 over 2 a t square. Now for we'll be solving the case 1 where time t equals to 1 second. So we can put t as 1 and a as 7.4. So this would be x is equals to 1 over 2, acceleration is 7.40, this is meter per second squared, and time we have 1 second, and it's squared. So this value comes out to be as 3.70 meter. So this would be the position of the object after 1 second. Now next we can solve the second case, B part basically, when time becomes 2 seconds. So when time becomes 2 seconds, we can use this equation. So this would be x is equals to 1 over 2, acceleration is 7.40 meter per second squared, and times this would become 2 here, so 2 second and it's squared. So this would become 4 multiplied with 3.70 meter. So if you observe that the distance becomes 4 times the initial distance. Similarly, we can solve the third case when time becomes 2 seconds. So x is equals to, we can use the same equation, this one. So 1 over 2 a, acceleration is 7.40 meter per second squared, times this would be 3 second and it's squared. So this would become 9 times 3.70 meter. Now the distance becomes 9 times the initial distance. So we can say that at time t equals to 1, let me write here, at time t equals to 1, the position of the body is at 3.70 meter. Now when time becomes 2 seconds, the position is 4 times this value. So this is 4 times this value, 3.70 meter. Now when time t becomes 3 seconds, the position is 9 times the initial value. Now here we observe one important thing, that the position does not change uniformly with time when object accelerates. Now since that this distance is different, like at 1 second the distance is 3.70, at 2 seconds the distance is 4 times of this number. Similarly at time t equals to 3, the distance is 9 times. So this the position is not changing uniformly. So let's do one thing. Let's try to plot the x versus t graph for this example. So we have plotted this xt graph, and these are the coordinates, that at time t equals to 1 second, the position is 3.70 meter. So 1 comma 3.70. Similarly at t equals to 2 second, the position is 4 times 3.70, which is approximately 14.8. And here this is time 3 second, and the position is 9 times this number, would be around 33.3. Now if we join these points with a smooth curve, it would be something like that. Now we see that this curve is a parabolic curve. Now one question for all of you, that why this curve is parabolic? Think and write the answer in the comment box below. Now next we'll derive the final equation, that is the fourth equation. So velocity as a function of position. Now the first equation that we derived, it was v is equals to v naught plus at, and the second equation that we derived, it was x is equals to x naught plus 1 over 2 times v naught plus v multiplied with t. Now from this equation we can write that t is equals to v minus v naught divided by a, and we can put the value of t here in this equation. So we'll get x is equals to x naught plus 1 over 2 multiplied with, this is v naught plus v, and t we have v minus v naught divided by a. Now we can do one thing, we can write this way as this is v here and this is v naught here. We can write this way also, it's one and the same thing. Now we can use one formula here. This is a plus b multiplied with a minus b. This would be a square minus b square. So this would become is equals to x naught plus 1 over 2. This would become v square minus v naught square divided by a, and this is equals to x. Now from here we can take this term to the left side. So this would be x minus x naught is equals to 1 over 2a multiplied with v square minus v naught square. Now we can take this term to the left side. So this would become 2a here like this. Now from here we can write that v square is equals to this is v naught square plus 2a times x minus x naught. And what is x minus x naught? This is the final position, this is the initial position, so this is delta x. So we can replace this term as delta x. So this is the fourth equation and the final equation of motion. Now let's take an question based on this equation. So this is the same question that I discussed in the starting of the video, and here we have to find the minimum length of the runway required for this plane, and this is the length of runway, delta xa. Now this direction we are taking to be positive, which is the direction of motion. Now since acceleration is constant, So we can use this equation, that is the final velocity is equals to v naught square plus 2 times a times delta x. Now in this particular case, the initial velocity v naught is 0 because it accelerates from rest. So this term would be 0, and the final velocity becomes vto, that is the takeoff velocity, and its square is equals to 2 times. Now delta x, in this case it would be delta xa. So from here, delta xa, this would be equals to v, this is takeoff speed and its square divided by 2a. Therefore we can say that the length of the runway should be equals to this value. And here we observe that since acceleration is constant, so we can write that delta xa is directly proportional to vto square. Now one question for all of you. Now think, what would be the minimum length of the runway if the same plane requires twice the takeoff speed? This time the value, this takeoff speed becomes 2 times of this. Then what would be the minimum length required for the runway? Think and try to write the answer in the comment box below. So this is all with this video, and in the next video we'll discuss the applications of the equations of motion that we've derived. So we'll meet in the next video. Goodbye.